Hello, everyone. My name is Andrea Yilling. I am Assistant Professor of Environmental Soil Chemistry here at Oklahoma State University in the Department of Plant and Soil Sciences, and I'm really excited to be a part of this session. I think there's a great lineup of speakers, and I apologize for delivering this as a pre-recorded talk, but happy to participate any way I can. So let's just jump into it. So this talk of mine is on the chemistry of using high carbonate irrigation water. And so for an outline of this talk, I'll start off with some context, definitions, and go over some of the well-known problems associated with high carbonate irrigation water, as well as clear up some of the confusion that sometimes arises when we're talking about water hardness and alkalinity, talking about where they overlap and sometimes do not. And as well go over the chemistry of the carbonate system, which can sometimes be a little bit intimidating. So I'm hoping to kind of demystify some of that for you all. And conclude talking about a subject that sometimes isn't covered that often in this kind of context, which is the carbonate contributions to soil carbon sequestration. And also, I want to note that I'm using an iPad here to kind of point. I have a pointer here, and as well, I'll be drawing occasionally. So for instance, here, I forgot to put in carbon. So soil carbon sequestration, you'll see what that will look like to be drawing on these slides. I won't subject you to too many of my bad drawings. I will try. Okay, so let's start off with water hardness and thinking about how hard waters are distributed in the US. So in this map here, we're looking at the more red, the more orange or red the color, the harder the water in that region. So we see the western half of Oklahoma has a higher prevalence of hard waters. And on the right, what I like about this diagram is it starts to break down the definition of water hardness into the component that is associated with carbonates and that which is just generally hardness associated with magnesium and calcium ions. And often these two go together, the carbonates and the magnesium calcium ions, which I'll go over in a few slides, but I feel like this is a good introduction to how hardness and carbonate are associated here. Okay, and the hardness that you are all probably familiar with is that which you experience, on your coffee pots, tea kettles, hot water heaters, in the bathtub, that scale that develops. Often the soap itself doesn't lather well, and that has to do with the calcium or magnesium in your hard water precipitating, reacting with the soap in a way that that soap is no longer able to do its job and interact with dirt as it's supposed to. And also under certain conditions like high concentrations of these ions or high temperatures, that can actually lead to the reaction of calcium with bicarbonate to form an insoluble calcium carbonate. So we have calcium interacting with bicarbonate. If you get high enough temperatures, they'll combine to form this precipitate. That's what you see as scale in your bathroom on your irrigation lines. Other issues, though, in soil systems and agricultural systems that are associated with hard water is higher pH soils. And so what I'm showing here is start on the left, a map showing where hard waters are located, hardness concentrations in aquifers across the state here, and we're looking at the darker the color of these dots, the higher the hardness level in these aquifers. So I mean, there's a lot of variability, but just generally notice that the western half of the state has a higher hardness level. And this tends to correspond more or less with higher pH soils in Oklahoma. So western half of the state tends to deal with these alkaline, greater than pH of 7 soils. And so you see this note at the bottom that in many soils, water alkalinity and hardness tend to be of common origin, which is why we tend to see them go hand in hand. Not always, but often, and especially in the state here where a lot of the kind of hardness comes from the carbonate containing bedrock, the kind of natural geology of these soils just supports the hard water, hard irrigation water. Okay, and so some on the left here, visible issues in our agricultural systems associated with high carbonate water is the precipitation again of these carbonates, where if there's enough of them in the solution, they will precipitate out and cause crusts and even clog your lines, and that can be problematic. What I'm showing on the right here is a bit kind of hard to interpret at first, but I'll walk you through. And this is showing some of the physical effects of high carbonate water that can occur. And on the top here, we're looking at a soil that was irrigated with fresh water, so it has very low to no carbonate. And on the bottom, this is a wastewater that was used to irrigate that has a very high carbonate concentration. And just the take home here is the difference in the pore, structural pore volume between these two soils. So think of that as the airspace, and the larger the soil pores, the better structure, and the more kind of air and ability to store water, all of the things that you want in the soil system. And the main line to compare is this top line, which is the top soil. As you see, it's much higher in the soil that received fresher water relative to this soil that received this wastewater, high carbonate water. You see that there's this big drop in the pore volume, meaning the pores became smaller and you have a loss of that soil structure that occurred. So this can happen in certain situations, depending on kind of the overall chemistry of that water. And so with high carbonate water, an issue as well is that if you have high enough concentrations, this can lead again to the precipitation, like I said, which means the removal of the compound from solution, from the soil water into a solid form. And so the sodium adsorption ratio, an indicator of that kind of sodium, the risk for dispersion and degradation in soils, is a relationship between sodium and concentrations of calcium and magnesium. And so if we have calcium and magnesium binding up with carbonates and precipitating out, it's lowering the amount of carbon and magnesium in soil, so in your soil water, in your irrigation water, increasing the relative amount of sodium and increasing the sodium adsorption ratio. Okay, and again, as you increase this ratio, you have here increased potential for dispersion. So in this case, we're looking at soil. These clouds here are showing how when you add soils with this problem, say an aggregate in this soil water, it'll disperse readily into all the many individual particles and lose that structure. And clearly do not want that to occur. So for some amount of carbonates are not a huge issue, but when you get it high enough, you get that precipitation, that removal of calcium and magnesium out of the solution, and the increase in relative amounts of sodium, okay? So let's go to definitions. I kind of started first with giving you some examples of the problems, but we need to define this because it does get a little confusing. Again, there's some overlap in terminology, where hardness, by definition, we're talking about the sum of polyvalent, here meaning polyvalent, meaning that the calcium has 2 plus instead of one single individual plus. So multiple positive signs here with calcium 2 plus, magnesium 2 plus, the sum of these cations in water, okay? There are other cations involved, but these are usually the ones of interest and of the highest concentration, okay? And there's 2 categories of hardness. There's the hardness that's due to calcium and magnesium carbonates, okay? So we have calcium carbonate here, magnesium carbonate here. When these dissociate and dissolve in soil water, they become separated into their ion counterparts. We have calcium and then their carbonate that's released in the process, okay? So here you can see how carbonate is directly related to hardness here, okay? But there's also non-carbonate hardness. So things like calcium chloride, magnesium sulfate also generate the calcium and magnesium ions, but we don't have that carbonate associated with it. And so total hardness is this carbonate plus your non-carbonate hardness. And generally, hardness is reported in equivalence of calcium carbonate, okay? Alkalinity and hardness are sometimes used interchangeably, but it's not always accurate, which is what I want to kind of go through here with you all. So alkalinity, by definition, is the measure of your water, your irrigation water's ability to neutralize acid, okay? So you add acid, something that adds H+ ions, hydrogen ions to soil, that if it's able to consume and remove that hydrogen ion that would otherwise create acidic conditions in your water, that is, it's neutralizing the acid, and it's part of this alkalinity concept. More alkaline, greater capacity to consume these acid forming ions, okay? And so to measure this, it's a sum of all titratable bases in a sample. We don't have time to go into that too much, but here its alkalinity is due to the presence of carbonate, bicarbonate, and hydroxyl ions. So you can see that overlap there, that the presence of these carbonates allows for soil water to consume those hydrogen ions and maintain a higher pH because you're not allowing the soil water to become more acidic. And part of the confusion as well is because this is also reported as equivalence of calcium carbonate, okay? And so there is some overlap, but I wanted to try to make clear, you know, what those differences are. And it really comes down to, I'll go back here, that non-carbonate hardness creates that distinction, okay? And so, of course, alkalinity here, due to the presence of carbonates, largely has a large influence over, say, the quality of irrigation water, as we're talking about in this session, and the mixing of some pesticides, how effective they will be. So really important to understand how, you know, how alkaline your soil water is. And of course, influences so many other processes and properties of your soil. And so how are carbonates measured in soil? And so it is very simple, of adding acid very slowly to your soil water, or a paste. But in essence, as you add that acid, it's transforming that carbonate into CO2, and you measure the amount of CO2 that's released as a measure of your carbonate in there. And so that this here is showing, before I talk about this fizz test here, that reaction where if you have calcium carbonate, and hopefully my pointer, there we go, it's a little slow, my laser pointer on my iPad, but if you have calcium carbonate and you add an acid, so H+ here, indicative of more acidic, or something that is an acid and produces hydrogen ions, that leads to the release of this calcium and then the production of CO2 gas. Okay, so that's the idea here with the titration. As you're adding acid, it converts the carbonates to CO2, and you measure that CO2 that's released. And what's really neat is that you can actually do a very simple fizz test or effervescence test to test for the presence of carbonates in your soil. So this is something you do to your soil itself, not the soil water, but you'd mix a bit of vinegar or a slightly stronger acid to your soil and see if bubbles form. And so if you have kind of a bubbling, visible bubbling occurring, that is a visual confirmation of the presence of carbonates. So very easy way of checking. But of course, there's ways of directly quantifying with this titration. Okay, and so there is, of course, this relationship with hardness and alkalinity, where the ions that are associated with bicarbonate and carbonate the bicarbonate and carbonate fraction of alkalinity are main cations responsible for hardness. So calcium carbonate, magnesium carbonate, when they dissociate, you have the calcium and magnesium that are responsible for hardness. And when you have hardness that exceeds your alkalinity, remember they're expressed in the same way with equivalence calcium carbonate. But if you have hardness that's beyond your alkalinity, that's your non-carbonate hardness. And I have a note here on the right that for the purpose of this talk, I'm really focusing on systems where your water hardness is dominated by your carbonate hardness. So in this case, hardness and your kind of carbonate problem are the same, okay? Just to also simplify things. Okay, and so some sources of high carbonate water. Well, hardness or high carbonate water is really a function of the geology of the area, where that surface or groundwater is located, and the dissolution of carbon dioxide from the atmosphere. So I will talk about that in a bit more detail. But first we have, the ions that are responsible for hardness are originating from these minerals that are very common in some soils here, like limestone, calcium silicate, that naturally produce these ions responsible for hardness. Rainwater is also naturally acidic and as well accelerates the dissolution or the breakdown of these minerals and the release of these compounds that contribute to your high carbonate water. And then as water moves down your soil, that's continuing to dissolve more CO2 from your root and microbial respiration. And this further dissolves or breaks down your minerals, okay? So we have here as an example, calcium carbonate. And if it's interacting with CO2 and water, you have the release of these calcium and magnesium ions and the release as well of your bicarbonate, okay? And so surface groundwater sources in areas with limestone are likely to have high hardness due to the dissolution of these bicarbonates and carbonates, okay? All right, so now for some drawing. So we need to talk about the carbonate system and chemistry of the carbonate system. And so I'm going to try to make this as simple as possible, but often the carbonate system is first easiest to discuss in the context of just surface waters. If you look up the carbonate system on Google, often this is the first image you see is a conceptual diagram of water where you have CO2 in a gaseous form that naturally enters the water, is dissolved in water to become an aqueous form, dissolved CO2 in that water environment, okay? When CO2 reacts with water, you get the formation of carbonic acid, okay? And I apologize for my handwriting. I'll try to make it as legible as possible. H2CO3 is carbonic acid. Carbonic acid is a weak acid, which means that it doesn't really like to stay together. It will readily split apart into, in this case, bicarbonate, HCO3 minus, and this also produces an additional H plus ion. Remember, that's what contributes to acidity, H plus, okay? Bicarbonate here is also a weak acid, and it will further dissociate into carbonate, okay? CO3 2 minus is what that says, I promise. Okay, and so what happens here is that if you have things like magnesium, calcium in your soil water already, which you likely do in many of these water aquatic environments, that will combine with your carbonate to form calcium carbonate. In this case is the example that I'll use, okay? And so often what's discussed in kind of aquatic environments is how when you have the formation of this calcium carbonate in water systems, the calcium carbonate can then settle down and become part of the sediment at the bottom, leaving these hydrogen ions in the water and leading over time to the acidification of water. So you might have heard of ocean acidification, and that is largely driven by this carbonate system. But in soil systems, especially here in dryland or arid or semi-arid environments where you have in some cases higher rates of evaporation, then you have precipitation or just not a lot of leaching opportunity, or these wetting drying cycles, that does not allow for that calcium carbonate to leach or leave the system, because this kind of settling sedimentation that I mentioned is a way that carbonate is kind of removed from that water, okay? But we have in our systems often this issue of this constant kind of replenishment and supply of carbonates, and in conditions that just allow for it to accumulate and stay in that soil water. So on the right here, I will draw what is occurring in soil environments. So we have the soil surface. We have, in many cases, calcium carbonate in the bedrock as a solid, right? Naturally there, and when it interacts with CO2 or water, you have the release, again, that dissolution or breakdown of that compound into, in this case, calcium, and you have bicarbonate, okay? And if you have a well that's tapping into that water where you have water interacting with the bedrock and causing the release of bicarbonate and calcium, that is what you're picking up when that comes back up and is used for irrigation, okay? And so you have at the same time, water that does move down that system. You have water, you also have CO2 from that just being dissolved in soil water naturally, but you have more of it because of microbial activity producing CO2. And yeah, it's just furthering that process of dissolution and breakdown, okay, as it moves through the limestone and increasing the rate of this process here, okay? And so the idea here is that rainwater, as it moves through, when you do have rain, then you have that picking up CO2 from the atmosphere. As that moves through soil, CO2 produced from decomposition is also adding to the CO2 concentrations. And the reaction of water and CO2 is also yielding more carbonic acid. And these will further dissolve the limestone and for example, dolomite, other carbonate-containing minerals that, as they dissolve, will release those carbonates, those bicarbonates, and pick up calcium, magnesium ions as well, okay? And so I want to mention briefly, I'm almost out of time here, is that the carbonate system is a buffer system, and that means that it can really resist change in pH. And it has to do with, in this case, it consisting of a weak acid and a conjugate base. And here the weak acid is, especially carbonic acid, is the main one of interest, where it will not fully and readily dissociate all the way. It will kind of move between fully dissociated and fully kind of together in its complete form, in its carbonic acid form, okay? And this allows for systems that contain carbonate to resist changes in pH. Okay, and so there are many natural processes in soil and management decisions that can kind of favor the production or reduction of carbonates. So I want to go back just to this reaction here, these three reactions that are involved in the carbonate system. If you have reactions that are leading to, say, acidification, so you have more, let me use a different color, more H+ ions, that will make this reaction go further to the left. But if you have, an increase in respiration because you have more microbial activity, then you have this going to the right. So there's a lot of different processes that can push and pull this in different directions, but because this is a buffer system, it's really able to resist change, and there's just this strong buffering capacity where it will maintain your soil water often above 7 if you have carbonates present. And so really the best way to deal with this is to remove the carbonates through leaching or degassing through acidification. So if you add enough acid, then you're able to push this reaction to the left such that you remove carbonate as in its kind of carbon dioxide product, okay? And that degasses and releases from the soil environment, okay? All right, so I am out of time here, and that's too bad, but what I do want to really quickly just go over is that, and I've mentioned the sodium hazard that occurs when you increase carbonate concentrations. It can lead to the precipitation of calcium and magnesium, so you increase that sodium concentration and the issues associated with that. But I also really want to briefly mention this residual sodium carbonate measure, which is another way to more directly understand your potential for precipitation and the removal of calcium and magnesium. So it's usually defined in this way, where you have your carbonate and bicarbonate added together, and you subtract from it your calcium and magnesium ions, their concentrations added together. And if this residual sodium carbonate index is greater than 2.5, then you have generally a high potential for precipitation, which leaves sodium in solution and increases the sodium hazard. Okay, and so I am out of time, but I just want to make a quick plug that there is also some interesting research on how high carbonate irrigation water actually can lead to increased soil carbon sequestration in dryland soils. So an interesting area of research that I invite you to go look into on your own, or anyone can reach out to me if they want to discuss any of these ideas further. So thank you very much again for the opportunity to participate in this session, and please do feel free to reach out with any questions at all. Thank you.